Welcome to the demonstration corner. Today we're going to demonstrate the ThermTest HFM-100. First, as customary, we're going to talk a little bit about the additional instruments that are in the demonstration corner, so that we can, we also offer live demonstrations on one-on-one basis as well as training. So we always like to give a little turn around the camera just to show all the equipment we have here. So we'll be talking about this unit today. This is the guarded heat flow meter, the HFM-100. This follows ASTM E1530 for measuring complex materials. It is guarded, so it has a wide conductivity range of 0.1 to 100 watts per meter Kelvin. So it's quite ideal for stacked materials or non-repeating layers through the thickness or heterogeneous samples. And this measures up to 300 Celsius. This is our MP1, which combines three methods: transient plane source, transient hot wire, and transient line source. This is our marquee transient method. MP stands for measurement platform, so it's the MP1. This has quite a bit of capability: cryogenic up to 300 Celsius, modular so that you can add up to 4 devices or 4 sensors, as well as a wide range of module capability to really allow it to be the marquee transient method in the industry. Separating out the individual methods for more simple applications, this is our TPS2 following ISO 22007-2. This goes from 0.01 to 500 watts per meter Kelvin. The comparison of that on the MP1 is the thermal conductivity range for the TPS on the MP1 is 0.005 up to 1800 watts per meter Kelvin. And the main reason for that is the shortest test time on the MP1 is 0.25 seconds. That's very critical to maintaining the basic assumptions and theory of the transient plane source method, which is to keep the heat within the body of the sample. So you need the variance of time. The longest test time is 1280 seconds. That's for measuring highly insulative materials. So you need that variance of time to be able to measure a wide range of thermal conductivities and dimensions. So this is our TPS2. It is following the ISO as mentioned. It has 2 ranges: 0.01 to 100 watts per meter Kelvin and 0.01 to 500 watts per meter Kelvin. And then just coming a little bit further is our THWL1. This measures thermal conductivity, thermal diffusivity, and specific heat of liquids. It's a transient hot wire method. It follows ASTM 7896. The key advantage of this method is the ability to back pressure it, so you can test at those higher temperatures past boiling points. You can back pressure it up to 20 bar or 35 bar. The further at the other end of the demo corner, which we're stretching the camera a little bit, that's our HFM-25. We did a demo on that yesterday. So that's our small heat flow meter, economical. It's built for small insulative samples on the scale of 2-inch square and down to 2 millimeters thick, as tall as 25 millimeters thick. So what we're going to talk about today is the HFM-100. In our demo corner right now, all we have is our HFM-100. There is one more model, and it is the HFM-50. The difference in dimensions are the HFM-100 can measure samples of 300 by 300 and thicknesses up to 100 millimeters thick. That's in the name. The HFM-50 is 200 by 200 and thicknesses up to 50 millimeters or 2-inch thick. So the reason for those different methods is there are industries that require measurements of a specific sample size. The HFM-100 is by far the more popular because it has the most flexible sample size. So in the case of heat flow meter, measuring a large sample is a strength, especially if you have highly heterogeneous materials like wall batting, or of course all kinds of insulation has different amounts of porosity, different sizes of porosity, different distribution, and captured gas. So the heat flow measures thermal resistance, and from the thermal resistance it calculates thermal conductivity. So if I open the chamber up, you'll see that there's an inside dimension equal to the largest that we discussed, which is 12 by 12 inch. And you can see that you would insert the sample. We'll go through this a little bit in more thorough, but what I want to talk about is the upper plate is what goes up and down. There's a motor in each corner of the plate along with a optical encoder that measures thickness. That's important so that we get an accurate measurement of thickness across the sample, as well as identify any non-flatness, so those motors know the position of each other, and they can identify non-flatness and alert the user to the non-flatness. And they will also reject a non-flatness at a certain tolerance. So the idea is that we want to make sure that we're measuring resistance across two planar surfaces as much as possible. There is two methods of measuring thickness. One is, as I mentioned, on a solid, rigid sample, we would get a thickness of measurement, average of 4 corners, on an XPS sample or any other sample that's rigid. The second approach would be for measuring materials that are compressible like this. You can tell the instrument to stop at a specific thickness. And that would be so that you don't want to compress the material beyond a specific point. You can, of course, measure at different compressions to enable different amounts of change in resistance due to change in compression or thickness. So today we're going to talk about, we're going to insert XPS and do the setup for that. Before I do, every HFM-100 comes with a piece of NIST 1450. The current batch is E, so it's a NIST 1450E. That is used for calibrating the instrument as well as verifying its operation. So you can run calibrations according to your company's SOP, or if you want to do it more randomly, you can do that as well. So we supply a piece of that with every instrument. The instrument can be run from the control pad. It is much more convenient to run it from the computer, but that capability is there. You can run full measurements from the keypad and collect data from that, but we'll be demonstrating the software. So for setting up a sample, you would want the flux sensor that's inside the HFM-100 is 4-inch square, or 100 by 100, and there's one on the top and one on the bottom. All the cooling and heating comes from Peltier tiles that are in several of them on the back side of each plate. And those Peltier tiles are chilled with a chilled recirculator. And that chilled recirculator is typically set around 10 degrees. But the overall temperature range of the plates is 75 degrees to -20. And that's the same for both the HFM-50 and the HFM-100. The mean temperature range depends on your delta. So if you're doing a 20-degree delta, that means your mean temperature range is 10 degrees above that. So it would be 10 degrees below 75, and then 10 degrees below that. So your mean temperature range and your delta on each side of that determines the full operating mean temperature. So for setting up a sample, we would insert it. We typically close the door at this point, but we'll leave it open. And actually, I'm going to go back to the software, so you won't be able to see this. But this upper plate will close as part of the measurement. So that's the full setup. I'll leave the door open anyway. Here you can see the desktop. And here's our main software for the HFM-100. We're going to go to run an experiment. Here's where we can name our sample. And we're going to load a calibration. So we've already run a calibration using NIST 1450E. And that pulls up all the calibration mean temperatures that we ran. And what's really nice about this software, this is quite a convenient software, is you can tell it to do one of all of them or an individual one that you desire. The other nice thing is if we want to do an assortment, we can cycle through that. So what that means is that in this case, it would do 50, 40, and 30 mean temperature, and then go back to 50 and cycle it one more time. That's a really nice way of looking at lifetime of your product to see if the installation changes with temperature cycling. But in this case, we're just going to do, basically we'll do all of them once. And we're going to leave it on auto detect. This is where you would change it from height if you had a compressible material. So in this step, you would say go to a specific thickness and the plates would stop at that thickness. But we're going to leave it at auto detect. That's all that's needed. So at this, what we're going to do is one for each one of these. And we're going to close plate. And when I click close plate, I'll go back and share the camera so you can see that step. So click close plate. So you can see the plate closing. And the plate does a double check on the thickness, so it actually closes, clamps, and then it'll lift off. I'm not sure you can see that. Then it'll close one more time to verify the thickness. And at this point, we would close the door and close it, so that setup is complete. Go back to the desktop, and you can see we're ready to start the measurement. So once the clamping's done, we click start and we tell it where to save the data. And the initial temperature, the initial mean temperature of 60 degrees with a delta of 70 upper and 50 lower will start to activate. So right away, the upper plate and the lower plate will go to their set temperatures. And on the right side, you can start to see those move and heat. And on the right side is the composite flux. So once a measurement gets the temperature, the plates get the temperature, and the heat flow becomes approaching steady state, the composite flux, which means it's a composite of the bottom and top flux, the average of those two is what's being displayed, and we're looking for a certain stability. That stability over time, it confirms whether a measurement is complete or not. So once that the status turns from complete, you'll see this be complete. You can see the thickness was measured at 49.52 millimeters. You can see the current temperatures. But what I can do, so we're certainly not going to watch this run, because each measurement of a 2-inch XPS would take 45 minutes or something like that, just due to the high resistance. Average test time of a 1-inch would be 30 minutes approximately. But what I can do is open up the software in another application and show you what this measurement set would look like, which I have here. So here's measurements done at means of 40, 30, 20, and 10. You can see that here. The upper plate and lower plates has a 20-degree delta. And here is our resistance values and our calculated thermal conductivity values. The 20-degree value is what you'll see spec'd on this material. This XPS is a couple years old, so you would have perhaps some effective degassing, but that's within 5% of the R value reported by the manufacturer. And that is essentially how the HFM-100 and the HFM-50 work. There's one more component that you can attach to this, which is the high TC kit. That enables you to extend the range of conductivity up to 2.5 watts per meter Kelvin. That's good for composites, plastics, cement, those types of materials. And there's another testing module you can add to this for running direct specific heat. So if you run direct volumetric specific heat measurement and you know the conductivity from the measurement, you can calculate diffusivity as well. So those are the add-ons you can add to it. There is a new version of the HFM-100, and it's called the HFM-100 HT, and that's for measuring high temperature. That will extend the range of the HFM-100 from -30 to 110 Celsius, the plate temperatures. And of course, your mean temperature is dependent again on the delta that you require across your sample. And that concludes the demonstration. Tomorrow, we'll be doing a demonstration on the HFM, or rather the GHFM. We'll talk a little bit about that method. But other than that, any questions, please contact us, and thanks for listening in.